Hello, welcome. So today we are going to read this chapter 21, which is on Optoelectronic Oscillator, given in the book Broadband Optical Modulator. Author or editors of this book are Entio, Chen and Murphy. So the reason why I am selecting this chapter or why the topic, because this optoelectronic oscillator is one of the important research area of Professor Vijay's research group, Vijay K. Das from IIT Madras. So, in order to know how he is working towards optoelectronic oscillator, this is the fundamental chapter which I would like to read and to know for wider understanding for our research scholars. So the chapter goes like this. 21.1 is about introduction, photonic RF oscillators, general architecture of optoelectronics, optoelectronic oscillator and COEOs. Then 21.2 OEOs characteristics means optoelectronic oscillator characteristics, optical gain of a photonic link followed by RF power generated by an OEO, oscillation frequency, phase noise, and frequency stability. After that, in 21.3, characteristics of OEOs and COEOs based on various modulator types. The OEOs based on an Jedi EOH and OEO based on an EAM electro-absorption modulator, a tunable fiber-based OEOs coupled optoelectronic oscillator. Then in 21.4 WGM EOM based OEO. WGM based tunable OEO. Then tunable OEO with a fiber laser. Packaged tunable OEOs. Summary and conclusion. That finally references. So introduction and authors of this chapter are Lute Maleki, Danny Eliyahu, and Andrew B. Matsko. So let us begin. 21.1 Introduction. The information age in which we live is powered by data flowing at ever increasing rates across a growing number of channels. Generation, transmission, and processing of this expanding data volume is regulated by the beat of the output signals are of RF, microwave, and as of late optical oscillators. Oscillators produce signals that are the carriers on which data are modulated. They set the clock speed in any data system. In radar system, oscillator performance determines the extent of capability for clutter rejection, and detection of small signal. In communication systems, oscillator performance determines the channel capacity and channel density. Since the range of application of the oscillator is varied, so are the types of oscillators that serve these applications. For example, the proliferation of small handheld communication devices and their associated frequency bands has created a demand for small, high-performance oscillators operating in the 1 GHz to 6 GHz band, with future systems likely to require higher performance at higher frequencies. On the other extreme, advanced radars that detect Slow moving targets in severe cluttered environment requires extremely high spectral purity at frequencies ranging from 10 GHz to 35 GHz to cover radar frequency bands. The technological areas of the applications mentioned above have their counterparts in scientific applications. Aside from being an integral part of physical sensors that measures various parameters of interest, oscillators have many applications in metrology and fundamental scientific investigations. These range from the measurement of the size of the particles in planetary rings to test of Einstein's general relativity. 21.1.1 Photonics RF Oscillator. The quality of signal produced by an oscillator generally depends on the energy storage element in the oscillator loop, which is typically a resonator or a delay line. Various physical relations of RF and microwave resonators have been used to address the specific need of each application. Quartz resonator, surface acoustic wave devices, microwave cavities, and lumped elements electronic circuits are examples of such resonators. The photonic oscillator is a new class of device that generates stable RF signals using optical energy storage elements. This class of oscillator became feasible as optical communication technology evolved and as commercially available components are developed or were developed. Typically, the photonic oscillator is comprised of the following stages. Number one, up conversion of RF signal to the optical frequency domain using a modulator. Second, translation of the modulated laser light through the optical storage element. Third, conversion of the modulated light back to an RF frequency using a fast photodiode. And fourth, closing the oscillator loop by feeding the RF signal back to the modulator. More stages such as amplification of the demodulated RF signal, RF filtering, or phase shifting can also be added. Such oscillators known as optoelectronic oscillators possess characteristics and performance parameters unmatched by their electronic counterpart. It is worth noting that an optical oscillator laser can also be used as a photonic RF oscillator. In such an oscillator, several harmonics are generated in a purely optical way. No modulators are involved. These kinds of device can be produced, for example, by locking the frequency of two lasers to two different modes of single optical resonator. In this scheme, harmonics are generated due to non-linear optical processes, such as parametric or hyperparametric or due to optomechanical processes. We do not discuss those devices in this chapter because they do not include the use of a modulator. 21.1.2 General Architecture of Optoelectronic Oscillator. Optoelectronic Oscillators and COUs. The OEO is a unique oscillator. OEO is a unique oscillator in that the equivalent quality factor in the oscillator loop can be selected to be very high, which is done by using an optical storage element such as a length of fiber or an optical resonator. This is possible since optical storage element, unlike their electronic counterparts, dissipate very little energy, ensuring that losses are small. The OEOs is also distinct from other oscillator since the frequency of the oscillation can be any frequency within the bandwidth of its component set by the center frequency of an RF filter. As such, the OEOs can serve numerous applications in communication and radar at frequencies limited only by the bandwidth of the modulator. Currently, all other components in the OEO loop can achieve higher bandwidth. In a conventional photonic link, an RF signal modulated on a laser carrier produces sidebands that are converted in a fiber waveguide and then recovered at the output of a photodetector. If the signal is a pure tone and the modulation is not of purely phase type, the modulated sidebands meet with the carrier on a photodiode to reproduce the tone. This simple link can be transformed into a feedback loop by applying the output of a photodiode to the modulator. This configuration functions as an oscillator if gain is introduced in the loop to overcome all losses. The oscillation initiated by noise in the system is self-sustaining if there is enough gain in the loop. This configuration shown in figure 21.1 is an OEO. The oscillator in figure 21.1 also includes a filter and a phase shifter. The phase shifter ensures that all wave propagating in the loop and in phase. Oscillation will be sustained for waves going around the loop one time, twice, m times, the number of which is determined by the bandwidth of the component in the loop. The filter selects a single frequency corresponding to a single mode of operation. Otherwise, this becomes a multi-mode oscillator. The OYO architecture described above is quite generic and can be extended to other configurations by the choice of its element. For example, the gain element and the filter shown in the electronic segments of the loop can be replaced with optical counterpart. A tunable filter in the loop produces a tunable oscillator. Multiple loops can replace a single fiber loop to produce added filtering to suppress any additional modes that fall within the bandwidth of the filter. While an intensity modulator is used in most applications, a phase modulator can also be used if the optical segment includes a dispersive element to convert phase modulation to amplitude modulation. So this is the figure 21.1 and schematic of an OEO. So there is a laser. Laser gives carrier frequency to modulator. So modulator is receiving carrier as well as RF signal. It gives the modulated signal to an optical delay line through the fiber, and a photodetector is connected at the output of this fiber, which converts electrical signal, equivalent electrical signal. Of course, uh, modulating signal will be here, and this is the RF filter which filter RF signal, high frequency signal. Then this is RF phase shifter and given to the RF amplifier to amplify this RF signal. And this is in the loop. Now this is the simple schematic of OEO. It uses optical modulator. The light source which produces the energy during the oscillation and shown to be outside the feedback loop in figure 21.1 can be brought inside the loop. This is accomplished by forming a second loop, this time around an optical amplifier to oscillate and produce laser light. Such a crude laser is then mode locked using the modulator in the loop driven by oscillation in the electrical segment of loop. This dual optical and electrical loop configuration is known as coupled optoelectronic oscillator. COUs. So coupled optoelectronic oscillator as shown in figure 21.2. Like the OEOs, the COEO has an electrical output and an optical output, but the COEOs produces a pulsed optical output as in a conventional mode-locked lesion, while the OEO's optical output simply carries the modulated tone. The performance of OEOs and COEOs depend on a number of parameters, including characteristics of optical and electronic component in the oscillator circuit. This depends this dependence has been previously analyzed in detail and described fairly widely in the literature. To be consistent with the theme of this book, we focus primarily on the role of the modulator on the performance of OEOs and the signals act it produces. Rather than producing a detailed analysis of every parameter here, we still describe the basic OEO feature to show how the efficiency of modulator, modulation bandwidth and response time, noise and insertion loss and optical power handling properties impact the oscillator performance. This chapter is organized as follows. In section 21.2, we present the basic equations describing OEO's properties using a generic model of the modulator. In section 21.3, we discuss performance of OEOs and COUs based on various types of modulators and various configurations of optical fiber delay lines. The performance of OEOs based on the whispering gallery mode modulators is studied in section 21.4. The discussion and conclusion are presented in section 21.7. So 21.2 OEOs characteristics. We considered OEO scheme shown in figure 21.1 to understand the behavior and characteristics of OEOs. We have to describe the properties of the photonic link and OEOs is based on 21.2.1 optical gain of a photonic link. The photonic link operates in the most efficient way if the modulator included to the link generates a single sideband. For an ideal single sideband modulator, the power of the output carrier PC out and sideband PS out optical waves is given by PC out, means optical output, and sideband PC. So PC out, that is the optical carrier output, divided by PC in input, is equal to 1 minus PRF in divided by PRF 0, or output divided by 1 plus PRF in divided by PRF O square. And this is output upon input. However, PS output upon P C means single sideband optical output is equal to 4 times of PRF divided by PRF output divided by 1 plus PRF in divided by 1 divided by PRF output whole square. Equation 21.1 and equation 21.2, where PRFO is the characteristics RF power of the modulator. Characteristics RF power of the modulator. PRF is the input RF power, and PC is the input optical power. These expressions determine the most efficient modulation process irrespective of the nature of the modulation. As they require conservation of the optical power, PC out plus PS out means optical plus single sideband is equal to PCE. To describe the photodiode in the OEO loop figure 21.1, we use the following phenomenological mode of the photocurrent. So photocurrent I is equal to RP, where R is the responsitivity. R is the responsitivity is equal to eta Q divided by H bar omega naught. Is the responsivity of the photodiode. Q is the electron charge. Eta is the quantum efficiency of the photodiode. Omega 0 is the carrier frequency, angular frequency. K is the angular frequency, and H bar is the Planck constant. Basically H by 2 pi is equal to H bar. P is the input optical power and P set is the saturation power of the photodiode. The saturation power P set is limited from above by the energy conservation law. According to equation 21.1, 21.2, the optical power absorbed by the photodiode is PCE. The time averaged RF power generation in and emerging from the photodiode is PRF out is equal to rho R square PC square into 4 PRF in PRFO multiplied by 1 minus PRF in divided by PRFO whole square whole divided by 1 plus P C in square divided by P set square plus into 1 plus PRF in divided by PRFO power 4. Question 21.4. Where rho is the resistance of the RF transmission line, we assume for now that the resistance of the photodiode is the same as the resistance of the RF transmission line. According to the energy conservation law, PC in greater than is equal to PRF out. It is convenient to parameterize the inequality equation 21.5 by introducing two parameters, that is PC in divided by Pset and PRF in divided by PRFO. It is possible to show that equation 21.5 is satisfied for any parameters value if P set is less than or is equal to 8 multiplied by within bracket 3 minus 2 root 2 divided by rho R square, where rho is the resistance of RF transmission line or photodiode. It is easy to see that P set is less than 43 milliwatt for R is equal to zero point 0.8, that is the responsivity is equal to 0.8 ampere per watt, and rho is equal to 50 ohm. Another useful expression Another useful expression that can be derived from the equation 21.5, this one, under the assumption that the modulator operates far from its saturation is 8 divided by rho R square PRF is greater than PRF out divided by PRF in is equal to G photon, which imposes a restriction on the gain G of photonic link. The photonic gain fundamentally cannot exceed unity if PRFO is greater than 250 milliwatt for R is equal to 0.8 ampere per watt and rho is equal to 50 ohm. To understand the meaning of the characteristics RF power of a modulator P RF 0, it is useful to consider a phase modulator. The power in the lowest order modulation sidebands of the modulator is given by P set plus minus out divided by P. So it is equal to pi by 2 into V by V pi whole square, where V is the voltage of RF signal fed into the modulator and V pi is the half wave voltage of the modulator. Keeping that in mind, PRF it is equal to V square divided by 2 rho m, where rho m is the resistance of the modulator. Comparing equation 21.8 with equation 20 1.2, and assuming that P set plus out plus P set minus out is equal to P sideband, we define the for the phase modulator PRF output is equal to V pi square divided by rho m into 2 divided by pi whole square. It is easy to find that PRF is almost equal to 200 milliwatt for a comparably large half wave voltage. V pi is equal to 5 volt and rho m is equal to 50 ohm. This means that if phase modulation is transformed to amplitude modulation without loss, the quite ordinary modulator based photonic link can have a gain larger than unity. However, the lower V pi is the higher the gain can be. One way to increase the value of the photonic gain is by using a trans-impedance amplifier that allows increasing the effective value of rho at the expense of a reduction in the reception bandwidth of photodiode. Larger rho results in a larger photonic gain in accordance with equation 21.4. This is an appropriate approach for a generic OEOs operating at low optical power. The photodiode in the OEO circuit should be sensitive to only a RF node, so bandwidth reduction is not a problem, but rather an advantage. However, this approach is useless if one employs a high power laser in the OEO circuit because the use of a transimpedance amplifier reduces the saturation power of the photodiode. Equation 21.6 and the maximal achievable photonic gain. Equation 21.7. It is important to highlight the generality of equation 21.6 and 21.7. The boundary values they describe do not depend on optical power falling on a photodiode. Hence, P set and G gain for photon gain stay unchanged if one introduces optical gain into the optical part of the OEO loop. Only the properties of the modulator and the photodiode determine the maximal value of the photonic gain. G photon. It is worth noting that experimental achievements of a photonic gain exceeding unity has been reported in several earlier works, 3 to 5. There is a way to increase P-set using a DC biased photodiode. Our theoretical model is not valid for biased photodiode because the energy conservation law should include the energy that the diode consumes from the DC current. Consideration of biased photodiodes does not change the results of our study significantly because the saturation power is small enough in fast biased photodiode and is generally less than 10 milliwatt. Moreover, a biased photodiode is equivalent to an unbiased photodiode and an RF amplifier. Therefore, such a photodiode introduces more noise into the RF signal. 21.2.2 RF power generated by EOS. To find the RF power circulating in the oscillator, we have to require unity gain in the closed OEOS loop. Gain of PR in PRF in into GRF multiplied by 1 plus gain optical photonic of R PR fin into PR fin divided by PGRF inverse is equal to 1, where GRF and PGRF are the net gain and saturation parameter of RF loop. The RF field circulating inside the optoelectronic loop is determined by saturation of either the optical or electronic part of the loop. Practice shows that making the RF loop saturate faster than the optical loop results in better OEOs performance. In this case, GPH of PR fin is equal to constant and the power leaving the fast photodiode is given by PRF out is equal to PGRF of GPH GRF minus 1. As a general rule, to have a reasonable amount of power in the loop, one needs the gain of photon and RF to be as large as 2 dB to 3 dB. Usually, such a trivial formula results in a reasonably good description of the experimental result. It is also worth noting that gain photon and gain RF are frequency dependent. So equation 21.11 should also be used to determine the frequency of the oscillation. The equation is insufficient, though to predict the frequency it should be used together with equation 21.13. Modulators are important elements for setting the OEM oscillation power as they determine the value as well as the RF saturation level of the photonic gain GPA. Low VPI modulators have low saturation levels, which eventually results in small RF power generated by the OEMs. Since RF power from the photodiode PRF out is usually less than RF saturation power of the optical circuit. The output power of the oscillator being a fraction of PRF out can be impractically low. For this reason, a significant post amplification is required in the OEMs. OEMs without RF application in the loop have been demonstrated. The basic drive for the development of such system results from the assumption that RF amplifier introduces 1 by F noise that significantly degrades the phase noise of an oscillator at low frequency. The power-efficient OEMs of this kind requires a very efficient modulators as well as a high-power photodiode. Additionally, amplifier-less OEMs operating at 1 GHz 7 and 1.25 GHz 6 were demonstrated. Very recently, a 10 GHz OEMs were also produced. It was shown that amplifier-less OEMs has better phase noise close to the carrier as compared to the conventional audio. However, the overall amplifier-less oscillator phase noise was significantly worse compared to the phase noise of conventional audios operating at a smaller frequency. In our opinion, there is no solid proof that an amplifier-less audio is better than a conventional audio, and this subject requires a more comprehensive study. With this, we shall meet again after break to read 21.2.3 and further. Thank you. See you soon.